Okay, Assalamu alaikum wa rahmatullahi wa barakatuh. How are you, gentlemen? So, inshallah, we are going to continue our discussion, control engineering, since we last stopped before week 8. So, if you remember, at the end of the last topic, we were talking about the modeling of control systems. So we have seen different graphical models, including the block diagram and the associated transfer functions. And then we later on discussed the state log graphs as another graphical means of modeling the system. And then we later on discussed that these kind of models only work with linear time invariant systems. And in order to have a more robust, versatile model that can describe systems that are not necessarily time invariant, we came up with the state space model, which is represented by the A, B, C, D matrices. So we have limited ourselves to electrical circuits. So we have seen how we can model an electrical circuit using the state space representation. So by giving any RLC circuit, depending on the number of the active components, we were able to come up with the number of states that are required in the circuit. And based on that, we were able also to use these states to come up with the state equations and the output equations. And based on them, we're able to extract the A, B, C, D matrices, which are used to model the system. So the new chapter now, chapter 5, which we are going to discuss in this lecture, inshallah, talks about the different operations that can be done on the state space representation. So we're going to be working with the A, B, C, D matrices, and you are going to be seeing how we can operate on them, how we can convert from one model to another, and we're going to see all these things, inshallah. So the way that we are going to conduct this lecture is we are going to use the slides, which I believe all of you have them already printed out with you. And instead of using the whiteboard, I'm going to use these white papers. So I'm going to use them as the whiteboard. And at the end, inshallah, I'm going to upload whatever I'm writing here on these papers. I'm going to upload them on the blackboard as well. So for each week, I'm going to create a dedicated folder in the blackboard. So in this folder, you are going to see the slides, this video that I am uploading, that I'm recording right now, in addition to the scanned notes that represent basically the whiteboard. So let's start. So yes, this is a revision of what we discussed before week number 8. So here we basically have a general case of a system that is modeled by these state equations. So you can see here we have x1 dot, x2 dot, x3 dot until xn dot. So here we have n number of states, and each state, as you can see, is written in terms of the other states, x1, x2, xn, in addition to the inputs. So here in this case we have more than one input. Right here you can see here we have the states vector x1, x2, x3 dot 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 until xn, and the state equations, as you know, we can write them in a vectorial form. So we can write them as a matrix. So we can say that d by dt x1, x2 until xn, which is basically x1 dot, x2 dot, x2 3 dot, equals to the A matrix multiplied by the states plus the B matrix multiplied by the inputs. So this we call this x dot. This is the A matrix. This is x. This is the B matrix, and here are the inputs. So the inputs, usually we are familiar with a single input, but we can have more than one input. So in this case, we have m number of inputs. So this is how the state equation matrix in the matrix form is written as x dot equals to ax plus bu. Similarly, we have the output equation. So you can have a single output equation if you have only one output, or you can have several output equations. So this is a matrix also. So this can be written as, for example, if I have two outputs, I can have y1, y2 equals to, if you remember, we can have, if I have also two states, I can write it, or three, if we say it, let's say it's three states. So it's going to be, for example, y1, let's say y1 is equal to 0, 1, 0, and y2 is equal to 0, 0, 1. Here I have x1, x2, x3. And let's say that these outputs do not depend on the input, so it means that the D matrix is equal to 0. So what does that mean? This means that y1 is equal to what? It's equal to x2. And this means y2 is equal to is equal to 0x1 plus x2, 0x2 plus x3. So it means that y2 only equals to x3. So yes, this thing is called the C matrix, and this is called the D matrix. So any system in existence can be given or can be modeled or can be described by these four matrices only. So this is nothing new. This is just a revision of what we discussed before the midterm exam. So the state space representation model, it means that any system in existence is going to be written in this form, or in a similar form to this one, but the difference is going to be in A, B, C, D, right? So what we did before week number 8, in the last chapter, we were modeling the electrical system by coming up with the state equations and the output equations. We were able to convert it into this vectorial form and coming up with these four matrices A, B, C, D. Okay. So just I'll give you a quick example on this. Similar to what we discussed in week number 8, if we had an electrical circuit, for example, the state space representation of that circuit could look something like that. I can have something like this: x1 dot x2 dot equals to, for example, R over L minus 1 over L, and here I have 1 over C minus 1 over C multiplied by x1, x2 plus, for example, 1 over C, 0, multiplied by U. And we assume, for example, we have a single output, and this output is equal to, for example, let's say it's equal to x1. So in that case, what do we say? We say y is equal to 1, 0, x1, x2, and it does not depend on the input. Okay, so this is something similar and familiar to us. We discussed this before. So just to refresh your memory and to see what we mean by these A, B, C, D matrices. So this is the B matrix, this is the A matrix, this is the C matrix, and this is the D matrix. So our work right now in this chapter is going to be dedicated on these matrices, how we can operate in them. So this is what we are going to be seeing inshallah. So we are going to, different operations are going to be required from us in this chapter. The first kind of operation or task is, how do I convert a transfer function to state space representation? Let me just adjust the focus. Okay. So in this task, we need to again. So as you can see here, I have a transfer function. This is similar to the transfer functions that you have been seeing since the beginning of the course. But if I have this transfer function, can I transform this transfer function into this model into the state space representation model? Basically, can I come up, if this is a system right here given by this transfer function, can I find what is the A matrix, what is the B matrix, what is the C matrix, what is the D matrix? This is basically what you need to do in this task. So to see the steps, what I'm going to be doing, we are going to be diving into the example right away. I'm going to explain on the example better than just reading the steps. So let's say I have this transfer function. Let me just rewrite it here. So I have y of s over u of s equals to 24 over s cube plus 9 s square plus 26s plus 24. Okay, so this is my transfer function. I need to find what is the A matrix, what is the B matrix, what is the C matrix, what is the D matrix. Basically, find the state space representation of this system. So how are we going to be able to tackle this task? So I'm going to show you first of all the step-by-step procedure, and then I'm going to show you a very handy way that you can right away get the answer without doing these all steps. Okay, so let's just first do the steps. So the first thing we're going to do, if I look at this system right here, Shabab, this is of course the transfer function, and as we know, the transfer function is written in the frequency domain. So the first step I'm going to be doing is I'm going to actually do cross product. All right, so if I do that, what do I get? I will get on the left side here, I will get y s multiplied by s cube plus 9s square plus 26s plus 24, and this is equals to h, it's equal to 24 u of s, right? I did the cross product. Okay, so I'm getting this. So y multiplied by all of that and 24 multiplied by this. Now what does that mean? It means that y is going to multiply by each of these terms, right? So this will give me what? It will give me y of s cube plus 9 s square y s plus 26 sy of s plus 24 y of s equals to 24 u of s. Well, in this case, u of s is the input, y of s is the output, right? Don't confuse this with the unit step function, right? This is just the input. So u is the input, y is the output, right? Because the transfer function is written as the output divided by the input in the frequency domain. So if you can guess what the next step, it's going to be actually, because this is in the frequency domain, when I say s multiplied by y of s, what does that mean? In time domain, it means this is what? This is differentiation. So this is first derivative, this is second derivative, this is the third derivative, right? Do you remember, ya shabab? So what I'm going to be doing, I'm going actually to take the inverse Laplace transform of all of this. So what I'm going to be taking, I'm going to take the inverse Laplace transform. So if I do that, what is s cube? Again, s cube means third derivative. So this basically means y triple prime, third derivative, plus 9 s square means what? It means I am differentiating y twice. So it is y double prime plus 26 sy of s means it is y prime, first derivative, plus 24 y equals to 24u. And notice here I'm writing small letters because this is the time domain right now, because by taking the inverse Laplace transform, I go from the frequency domain to the time domain. Okay, Shabab, is it clear how I hope it's clear that how I reached this step. Now remember, in order to write the ABCD matrices, what I need to do is what the A matrix is the most important one, obviously. So the A matrix is the most important one to be able to get. And the A matrix, remember, just to point out here, the A matrix is what? The A matrix is basically, I have the states like this, right? So I'm going to have the states like that. Here I have the A matrix, and it's going to be multiplied by the states themselves, right? So in the state space model, we have the derivative of the states equals the A matrix multiplied by the states, right? So this is what I need to do now. This is my system in the time domain. This is the differential equation that governs the system in the time domain. And as you remember, just to refresh your memory, if I have s cubed here, it means the system is third order. Why do we say the system is third order? Because the system relies on the function itself, or it depends on a variable and depends on a first derivative, a second derivative, up to a third derivative. So third order means the system depends on a third derivative, like we have here. Okay, Shabab. So the system here, if I ask you, if you remember the term state, what does it mean? The state is basically a variable that the system that I need in order to describe the state of the system, right? So state variable, by knowing what are the state variables of the system, if I know what are the states of the circuit or the system right now, I can tell you what is going to be the state of the system at any point in the future, right? This was the definition of the state. So in the example of the electrical circuits, we always choose the voltages of the capacitors and the currents of the inductors as our states, because by knowing the voltages of the capacitors and the currents of the inductors, I can predict what are going to be the future values of the whole circuit, so the state of the circuit at any point of time in the future, right? That's why these states are very, very important. And this is something that we are going to be learning, inshallah, in this chapter as well. In this lecture, we are going to see, by knowing these states, by knowing A, B, C, D, how can I know the future states of the circuit at any point of time? So let's get back here. So what I'm going to do, this is typical issue. So if I have now, since I have the differential equation, if you have a differential equation that governs any system, then this is how you do. First, you go to the variable itself, which is y in this case, and choose it as your first state. Okay, Shabab? Again, once you have a differential equation of any system, always go for the variable itself. Okay, the variable, not the differentiated variable, the variable itself. Take it and assign it to be your first state. Okay, it means that this system, it means this system depends on y, of course. So y is an important variable to describe this system clearly, because it's part of the differential equation. So what do you think is going to be the second state variable that I have to choose here? It is going actually to be y dot. So this is going to be your x2. What is going to be my third state? It's going to be the second derivative. This is x3. Okay, sure. So in this case, if I have a system like that, see, I have a third order system, right? Just like an RLC circuit. If the circuit has, for example, two capacitors and one inductor, if the circuit has two capacitors and one inductor, it means how many states do I need to present the system? It means I need 3. And what is the order of the system? It's going to be third order. So right now, how many states do I need for this system? I need 3 states. Okay, so I'm not going to once somebody can come and say, "Khalas, I'm going to choose this as a 4th state." Yeah, you can do that, but this is redundant. Okay, this is not going to give you any new information. I don't need to know what is this in order to describe the whole system. I'm going to show you why in a moment. Okay, this is a 3rd order system. I have up to the 3rd derivative. It means I only need 3 states. See, I have s cube. It means I need only 3 states. What is the first state? Always choose the variable itself as your first state. The first derivative, your second state. The third derivative, first derivative, second state. Second derivative, your third state. Now what happens? Let's assume a system هنا مثلا can s to the power of 4. How many variables do I need? How many state variables do I need to choose? In that case, I would need to choose 4 variables. But right now, I only need 3. So I'll start by that: x1, x2, x3. Right? So what I'm going to do, I'm going to come here. I will say set x1 equals to y. Set also x2 equals to, what did we say? It's equal to y prime. But wait a minute, y prime is the derivative of y, and y itself is x1, right? So what I'm going to do, look here, instead of writing y prime, I'm going to take out y and write x1 instead. So I will say x2 equals to x1 prime. So I have x2 equal to x1 prime. Or instead of writing prime, I can say it's x1 dot. See what I have here, Shabab? I have a relationship between x2 and x1 dot. This is very, very important. How about x3? x3 is equal to what? x3 is equal to y double dot. Do you agree? Y double dot. Which is equal to it is equal to y double dot. This is the second derivative of y. Or it is the derivative of the derivative of y. This is the derivative of y, right? So y double prime, it means it is the second derivative of this or the first derivative of this. Right, Ishma? So I can say x3 equals to y double prime. But y double prime is equal to is equal to y prime, right? Prime. And y prime is x2. So I can write x3 equal to x2 prime. And this is obvious, right? Look here. x2 dot, x1 dot, when I take y is x1, right? Y, x1. When I take x1 dot, it means it is x dot, or y dot. But y dot is x2, right? Y dot is x2. Now this x2, if I differentiate this x2 again, what is it going to be? It's going to be x2 dot, or y1, y prime, differentiated again, it becomes y double prime. يعني ايش؟ يعني x2 dot is x3. x2 dot is x3 and x1 dot هي x2. All x is y itself. Why is that important? Because by having these, now I can almost write the state equations. So what I'm going to write here, I have x1 dot, remember the state equations, this is what I need: x1 dot, x2 dot, x3 dot. Right? So what is x1 dot? Look here, x1 dot is x2, right? So x1 dot is x2. How about x2 dot? x2 dot is x3. So what do you think is the only remaining task for us to find now? The only remaining task is to find what is x3 dot. Where am I going to be getting x3 dot? I'm going actually to be getting it from here, from the differential equation itself. So always in this kind of questions, in these kind of problems, always x1 dot, x2 dot are going to be very easy to find, right? Always x1 dot is going to be your x2, and x2 dot is going to be your x3. You can actually blindly do that, right? Because always we have, because this is the systematic way that we have followed, which shows y to be our first state. That's why it is, and we chose its first derivative to be the second state, and second derivative to be the third state. And because of that, when I differentiate that, I get x2 because I chose it to be my second state. And when I differentiate this again, I get the third state because this is what I chose to be my third state. That's why x1 dot and x2 dot are always going to be like that. Very straightforward. x1 dot is x2, x2 dot is x3. Now how about x3 dot? Again, in order to get x3 dot, I need to work on this differential equation. Right? So what I'm going to be doing, I will go to this differential equation. I'm going to rearrange it. Look, what I need to find. I need to find what is x3 dot. What is x3 dot? If I differentiate this x3, what do I get? Now let me just remove this so that it does not confuse us. What do I need to get? I need to get x3 dot. It basically means y double prime differentiated again. What it becomes? It becomes y triple prime. Right? So if I differentiate this y double prime, if I differentiate it again, it becomes this. So I will put this in one side, put everything else on the other side. So I'll come here. Let me come here. What I'm going to say, I will say y triple prime is equal to what? Now move everything to this side. So what am I going to be getting? I will get minus 9y double prime plus minus, right, 26y prime minus 24y, right? Move everything to the other side with the negative sign, and I have here the original 24u. Okay? But instead of writing these like this, if you notice, y triple prime, as we said, y triple prime is the derivative of y double prime. And y double prime is x3. So what is this? This is x3 dot, which I need here, right? How about y double prime? Y double prime is what? It is x3. So this means this is minus 9x3. How about y prime? Y prime is x2, right? Y prime is x2. So I can say minus 26. Y prime is x2, right? Y prime is x2. Minus 24. What is y? It is x1 plus 24u. Okay, so remember that a state equation, I need everything to be written in terms of states or inputs, and this is what I have here. But instead of writing it in this order, I'm going to actually rearrange it. I'll make it such that x1 first, then x2, then x3. So I have finally obtained my state equations, which is the most important part. State equations. So what is the output equation? The output equation is, what is y? So I need to write y, the output, in terms of, y is the output, I need to write it in terms of the states. And what is y? Look, what is y? What is y? Y is x1, right? So I can simply just say y is x1, that's it, right? There's no input, there's no any other states, that's it. So the output equation is just very straightforward like that. Since now I have my state equations, I have the output equation, I have basically solved the whole question, right? So what do I need to do now? Instead of writing it in this form, again, we need to write it in the matrices form. So this is what I'm going to write. I need to write it in A, B, C, D. So this is what I'm going to write. This means that x1 dot, x2 dot, x3 dot equals to what? Now be careful here, look here. x1 dot equal to x2. So how do I write that? Remember, this is going to be something like this, multiplied by x1, x2, x3 in this order, right? Plus something multiplied by the input u. What is x1 dot? x1 dot is equal to x2, so it's equal to ايش? 0 1 0, right? 0 x1 plus 1 x2 plus 0 x3. So basically x1 dot equals to x2. How much u do I have here? Nothing. There is no u, right? So what do I put? Put 0. Okay. How about x2 dot? x2 dot is equal to x3. So what do I put? x2 dot is equal to 0 x1, 0 x2, x3. How much input? No input. Right? Finally, how about x3 dot? x3 dot is ايش? It is minus 24 x1 minus 26 x2, so minus 26, and minus 9 x3. And still I have also 24 u, so 24 u, like that. So what does that mean? Yeah, before we discuss that, let's also talk about the output equation. So the output equation, how do I write it? I write it as y equals to, it's equal to ايش? Only x1, so it's going to be written as as such. Here I have x1, x2, x3 plus something multiplied by u. So y is nothing but what? Y is only equal to x1. So how do I write that? Say y is equal to x1 plus 0 x2 plus 0 x3. You agree? And how much input do I have here? Nothing, so it is 0. Okay, so this is the final solution that we have here. This is the state space representation. This is the B matrix. This is the A matrix. This is the C matrix, and this is the D matrix. So now I have gone from the let me just make this clear. Cube. I've gone from the transfer function to write it in the form of state space representation, A, B, C, and D. Now, if we go back to the actual, yeah, before we do that, yes. So here you have the steps here is written in the slides again. So here you have a notice here, right? If you notice, if you compare the output, this our solution here, if we compare it to the question itself, to the transfer function given in the question itself, what can we notice? First, log ratio 9, 26, 24, right? What do we have here? Minus 9, minus 26, minus 24. And this is actually always going to be the case, all right? So all these steps, you see all these steps, you don't actually need to do them. And this is quite typical. By giving only the transfer function, this is what I can do. Look, so instead of doing all these steps, I can come like that. I have this question here in front of me, right? So if I see this in front of me, this is what I'm going to do. I'll say this is my, let me write it here right away. So by saying this is my transfer function like that, this is what I'm going to do. So I will say A is equal to, remember how it was, because remember here, right here, always we said that x1 dot is going to be your x2, right? And x2 dot is always going to be your x3. That's why always x1 dot is going to be, look here, x1 dot x2, x2 dot equals to x3, right? So blindly, without looking at anything, I can just come like that. I will say A is equal to let me, instead of writing A, I will write it like that. I will say x1 dot x2 dot x3 dot. See here, I know that I'm going to have 3 states because this is a third order system, right? So it's always this is multiplied by x1, x2, x3 plus something multiplied by u. And the y matrix is going to be something multiplied by x1, x2, x3 plus something multiplied by the input again. So right here, blind, without doing all these steps that you have here, without doing all these steps, I can just by looking at this, I will look at the denominator right here. So this is how I'm going to fill the state space representation. I will say x1 dot equal to x2, right? Then x2 dot equal to x3. See? x1 dot equal to x2, x2 dot equal to x3. Always going to be like that. Any system will be like that. The only difference is going to be here. Right? So by looking at this transfer function, I can fill this one. How am I going to fill it? I will do two things. I'm going to take these elements, I'm going to flip them, flip the order, and flip the sign. So look here. Here I have, so what I'm going to put here, I'm going to put the 24. And I'm going to put it with a negative. So it will be minus 24. Then the next element, I'll move like that. So here I put 24, minus 24. So here I'm going to put minus 26. And here I'll put minus 9. See, without even doing all these steps, we're getting the same answer like here, right? So this is how I get this. How do I get the B matrix? I get the B matrix from what I have up here. So always this is going to be 0, and this is going to be 0. Always. This is the only thing that's going to be different. So what is the value that I'm going to have here? It will depend on what I have in the numerator. Here I have 24, so here I'll put 24 also. Okay? How about the output equation? The output equation will always be like that. It will always be, because remember, we always choose y to be our x1. We always choose this to be our x1. That's why y will always be 1, 0, 0. And 0 here. I didn't even need to look. So this is fixed. This is fixed, right? For any system, for any differential equation, it's going to be like that. The only difference is going to be this. So what do I need to do here? This will be 0. This will be 0. And the value I have here, I get it from here, right? So this value, I get it, put it here. And this always fixed. 0, 1, 0, 0, 0, 1. This is fixed. The only difference is going to be in this one. How do I get this one? I get it from the denominator here, these three elements. But what do I do? Flip the order. So put minus 24 here, then minus 26, then minus 9. And of course you flip the sign. So minus 24, minus 26, minus 9, like that. So any system is going to be like this. So now it's up to you if you want to do it like the detailed way like that, but it's quite typical just to get it right away like this, right? So let's now move to the next subject of this lecture. I hope this was clear. I'm going to post a homework, inshallah, on these kind of processes so that we can have practice on them. So just to conclude the show, just to summarize what we did here, so that we can keep it in our mind. What we did now, the first operation that we have learned so far in this lecture is, if I have the transfer function, how can I get the ABCD matrices? How do I get the state space representation? So we are moving from the transfer function to state space representation, right? So this is the topic of this part, right? So converting a transfer function to state space. This is what we did right now. So, and this can be said on converting a transfer function to state space representation. Or instead of giving you the transfer function, he can give you the differential equation right away. Right? So it's the same thing. He can give you the transfer function the differential equation right away, or he can give you the transfer function. So whether he gives you this or this, now we should be able to get the differential equation. Not differential equation, to get the state space representation. Right? So we have learned how do I get the state space representation from the differential equation or from the state space from the differential equation. Or from the transfer function. Right? So transfer function to state space, or differential equation into state space. Okay, these are the things that we have learned so far. How do I convert the transfer function into a state space representation? How do I convert the differential equation form like that into state space representation? It's basically the same thing. And this is one step easier because you don't need, it's already giving you the differential equation. Okay, sure. Now let's move to the next topic of this lecture, which is very, very important. And it's called the state transition matrix. Remember, ya shabab, we said that the definition of a state, the state is the variable in the system that by knowing these variables of the system, I can now predict the situation or the whole state of the circuit at any point in the future. Right? So if I have a circuit like that, for example, if I have a circuit like this, right? Let's say I have another resistor here as well. So this is R2, R1, this is C1, this is L1. Okay, this is the input. Okay, let's say this is Vn. So this kind of circuit has a lot of variables. I have VR2, I have VR1, I have VC1, I have VL1, and I have the currents as well. I have IR1, IL1, IC1, IR2. Right? So we said that in order to, but I don't need all these, I don't need to know all these variables to know or to describe the system or to describe this circuit, right? We said that if I have an RLC circuit like this, actually I only need two variables. What are these two variables? They are VC1, the voltage of the capacitor, and the current of the inductor. And we call them, these are the states. State variables or simply the states. Right? So if I know these, I can now know the future values. If I know if I know what are the initial values of these two things, what are the initial value, what is the initial voltage of the capacitor, what is the initial current of the inductor, I can now tell you the whole state of the circuit in the future. Okay, as if I'm predicting what the future is going to be. How I'm going to do that? Actually, you know that you do that by the state transition matrix. Okay, the state transition matrix. Look at what does the word transition mean? Transition means moving from one state to another. And this is exactly what we want to do, right? I need to know VC1 and IL1. If I know the initial conditions, if I know VC, for example, if I know VC1 at time equal to 0, what is going to be VC1 at time equal to 5 seconds, for example? If I know the initial condition, how much is going to be the next value? How much is going to be the value after 5 seconds? How I'm going to move from here to here? Using the state transition matrix, right? So this is why we need the state transition matrix. Similarly, if I know what is IL0, if I give you what is IL0, what IL1 of 0, how can I know the value of this current after 5 seconds? Is it possible? Yes. How do I move from the initial condition to this point? Using the state transition matrix. And if I know what is VC1 and IL1 at any point of time, I can use this information. If I know these, I can know what is this, just using the regular circuit laws and equations that I'm familiar with. KVL, KCL, Ohm's law, and so on. Right? So our challenge now, or our task, or what we need to learn now, how do I get this state transition matrix, which is very, very important. Okay, so in order to find how to find the state transition matrix, let's follow the following derivation. And the derivation is not important, but I'll just show you the steps that we have here, right? So remember, any system is going to have this state equation, right? It's going to have x dot equals to, let's say it is x dot. So yeah, so the any system is going to have this state equation, x dot equal to ax plus bu, right? Plus bu, right? This is the state equation, right? This is a matrix. What is this? This is x1 dot, x2 dot, and so on. And this is x1, x2. This is a matrix. This is a matrix, right? Now let's assume b is equal to 0. In this case, we don't have an input. So what does that mean? What does b equal to 0? It means that the derivative here, this does not depend on the input, right? So x1 dot does not depend on the input, x2 dot does not depend on the input, x3 dot does not depend on the input, and so on. Nothing depends on the input. So if I have this particular, form that I have here, x dot equal to ax, let's take the Laplace transform of both sides. So if I take the Laplace transform of both sides, what do I get? Remember, Yashua? Again, derivative means you multiply by s in the frequency domain, right? So this will be s x of s. But don't forget, I have also to subtract dash the initial condition, right? Remember? Laplace transform of d of y of t by d of t equals to what? It's equal to s y of s minus the initial condition of y, right? So this is basically what I did here. I just took the Laplace transform of this. So I'm getting this. How about that? This will be just a x of s, because a is a constant, right? So this is what I get. Now what is the next step? You can guess the next step that I'm going to do. I'm going to move this to the other side and take it as a common factor. And then move this. I can move this to the other side here. So what do I get? I will get x of s multiplied by, what do I get here? I have s. When I move this here, it becomes what? It becomes minus x of s. So if I take x of s a common factor, so it will be s minus a equals to what? This will move to this side, so it will be x of 0. What is this x of 0, by the way, Aisha? These are the initial conditions of all the states. And for example, if I have 3 states, so this is what? This is a matrix that looks like that. This is a matrix that looks like this. x1 of 0, x2 of 0, x3 of 0. Yani this tells me what are the initial conditions of all the states. And for example, what is the initial voltage of the capacitor, first capacitor? What is the initial current of the second inductor, or first inductor? What is the first current in the second inductor, right? For example, if I have, for example, one capacitor, and 2 inductors. Okay, so this tells me what are the initial conditions of all the states. Now I need to move from this to any point in time. I want to know this. I need to know what is x1 of t, x2 of t, x3 of t. I need to have a formula or an equation that tells me this is what x1 of t is. This is what x2 of t is. This is what x3 of t is. Now, if I want to know x1 after 5 seconds, what do? Put 5 instead of t. Well, we're going to see that this right now, inshallah. Okay, but now we have a problem right here, right? See, the problem is what is this is the A matrix. What is this? This is the variable s. This is the complex frequency. So can I just subtract a constant or a variable like that, a scalar variable like that, minus a matrix? I cannot. So if you remember from engineering mathematics, the way that you tackle this issue is to do what? You basically multiply this scalar by the identity matrix. Remember what is the identity matrix? The identity matrix, which you call I, is equal to 1, 1, 1, 0, 0, 0, 0, 0, 0, right? if it's a 3 by 3. If it's 2 by 2, it's equal to what? It's equal to 1 1 0 0, right? This is the, call it the identity matrix. So right here I cannot do that. This is not allowed. So what I'm going to do, rather than just saying s minus a, this here we have here an issue, so I'm going to write it like that. X of s is equal to si. So I'm basically multiplying s by this. So what is going to be si in this case? If I multiply si, what do I get here? It will be s0 0 s, right? Multiplying s by that. I multiply s by this. So s 0 0. Now it becomes a matrix. I can subtract a from it. Now which identity matrix do I use? Do I use this one or this one? It depends on the size of a. If a is 2 by 2, you use this. If the size of a is 3 by 3, you use this. Okay? So it's I minus a. Oh, sorry. Here common factor. We don't have equal here. So x of s equal multiplied by si minus a equals to x of 0. Now what do I need to find this? I need to keep x of s in one side, and I will need to move everything to keep everything else to the other side. So usually if we have like scalar equation like that, how do you do that? We basically divide by this, right? But remember, now I have matrices. I cannot divide by a matrix. So division by matrix or division by matrix. How do we do the division by matrix in like how we do it in engineering mathematics? So dividing by matrix basically means multiplying by its inverse, right? So like in regular algebra, I can say 1 over x is the same as x multiplied by minus 1, the inverse, right? Same thing. But I don't have this in matrices, right? So this is the form that I need to write. So what do I say? I say x of s multiply, so it's going to be si minus a multiplied by the inverse of this on both sides. I want this to go away, right? I want x of s to be here alone. So I'm going to multiply by, I'm going to multiply by the inverse. Now be careful, Isha. When you talk about matrices, the order of multiplication is important, right? So I'll multiply the inverse on the left, like this. This is, I'll just leave this outside. This is a scalar, so I'll keep it out. Not a scalar, sorry. But it is not, I will leave it on one side, right? So I'll just leave it like this. And here I have minus 1 multiplied by si minus a equals to, same order. Look, this was in the left. So it would be si minus a inverse multiplied by x of 0. Right? So what does that give me? This would cancel away with that, right? The inverse multiplied by the matrix itself, they will cancel with each other. It will give me the identity. So what do I get here on the left side? I get x of s. So x of s is equal to x of s is equal to si minus a inverse x of 0. So look here, Ishab. This thing, what look if you look carefully at this form that we have right here, the thing, this part of the equation, what does it do? Look, here I have the initial conditions. I take these initial conditions, multiply it by this part, this quantity, I get x of s for any value of s. Okay, can you see what happens now? By knowing what are the initial conditions, what is the initial voltage of the capacitor, what is the initial currents of the inductors, multiplying by this quantity, because I know what is the value of x of s for any value of s. حط أي s, put any s here, you know you can get the value that you want for any value of s that you need, just by knowing the initial conditions. And this is exactly what you want. That's why this thing is called the state transition matrix. This whole thing is called the state transition matrix. Look, and it's called phi of s. This is a symbol. State transition matrix. So don't worry about this derivation. This derivation, don't worry about it. This is the form that we want. We need to know that 5s equals to what? We need to know that 5s is equal to si minus a inverse. This is what you need to know. How we got this? Get this form? This is the derivation that we did. Very simple derivation, as you can see. But I want you to appreciate the importance of this. Look, this means what? It means, let me bring this here. This means what? It means that give me the initial conditions, multiply the initial conditions by this quantity, which is called the state transition matrix, not quantity, by this matrix. If you do that, خلاص, you get the value, you get the states, the value of the states at any frequency you need. Now we're almost done. Remember, Aisha, this is not exactly what we want, right? What we want is actually to find x1 of t, x2 of t, x3 of t. اللي هي ايش? This is x of t, right? I need to know that I will need to find this matrix. This one is what? This is not x1 of t, x2 of t, x3 of t. This is this one that I got now. X of s. This is x1 of s, x2 of s, x3 of s. I don't need to know, I don't want to find x1, x2, x3 in the frequency domain, right? This is x1, x2, x3 in the frequency domain. This is what not what I want. Remember, our goal is to find the time values, the future values. When we talk about future, we want to find the value at any point of time, t, right? So that's why the last step that I need to do here, I need to convert this from x of s to x of t. And how do I do that? I do that by taking the inverse Laplace transform. So if I take the inverse Laplace transform of this, what it becomes? It becomes x of t. Right? And how about this? These are constants, right? Remember, these are the initial conditions. These are constant values, right? So these are constants. So I can just take them out of the inverse Laplace transform operation. So what does it mean? It means that x of t يساوي ايش؟ يساوي initial conditions multiplied by the inverse Laplace transform of this, which we can call it phi of t. Okay, so you can say x of s is equal to phi of s x of 0, أو x of t يساوي phi of t x of 0. طيب, we know phi of s. We know phi of s is equal to si minus a inverse. It means what is phi of t? Then phi of t is going to be the inverse Laplace transform of this. So it's equal to the inverse Laplace transform of si minus a inverse. Okay, this is our state transition matrix. This is the state transition matrix in the frequency domain, but this is the one that we need because we need x of t. We don't need x of s. We need to know what is x of t. That's why we use this one, right? So don't get intimidated. This is very simple, as you're going to see, inshallah. We'll solve many examples on that here in this lecture, inshallah, or in the homework as well. Right? So here is basically the steps that we have shown. In this slide, this is just for information. He's saying the different ways you can get other ways you can get the value of phi of t, the state transition matrix. So you can use the Taylor series expansion, right? So don't worry about this. Okay. So what we did right now, ya shabab, is for this kind of system. لما يكون السيستم when the system is written like that. So what is the special thing about the system? The special thing about the system that the value of b is equal to 0. What does it mean? It means that the states, look, the derivative of the state does not depend on the inputs. It only depends on x. Yeah, that's why I'm only considering a. If the system is like that, look here, if the system is like that, then it becomes a little bit more challenging. شوف لما يكون السيستم when the system is like that it's very easy. If you want to know what is the value of x of t, خلاص give me the initial conditions and multiply them by phi of t. That's it. Give me the initial conditions, multiply by phi of t, the state transition matrix, you get x of t at any point in time. Okay, so if this is the system like that, if the system is written as x dot equals to a x, right? But what happens if the system like that? Now if the system is not like this, but in addition I have plus bu here. Why don't I have bu again? Because bu, in this case, b is equal to 0. Okay, so in our analysis, we are always going to be dealing with systems that b is equal to 0. So this is always going to be our case. But for your information, يعني, if b is not equal to 0, then this is the term that you are familiar with, right? This is what we saw here, right? X of t equals to x of 0 multiplied by the state transition matrix in time domain, right? But if b is not equal to 0, then you have to do this, multiply by this integration. يعني, this is just for your information, don't worry much about it. Okay, sure. So this is the important part that we need here. Inshallah, with examples, things are going to be clearer and more understandable. لاحظ هنا يا شباب, look here. This is an illustration of this transition matrix action. Look. If you know what are the initial conditions, look here. What is xt of 0? These are basically x of 0. These are the initial conditions. The initial conditions. If you know this, and you can find what is phi of t, here the state transition matrix, now you can know what is going to be the future values. If I want to know what is going to be the states, what are going to be the states x1 or x2 or x3 after, for example, 5 seconds, how do I move from 0 to 5 seconds? I multiply by ايش? phi of 5. How do I go from here to here? Here I have x of 0. You multiply them by phi of 5. You go here. You know what is the values after 5 seconds. But what if you want to find, for example, after 12 seconds? What do? Again, you take the same initial conditions, x of 0, then you multiply them by phi of 12. So instead of substituting with 5, قيمة t هذه, لا, you substitute with 12. So you transition. You move the initial conditions of the states of the system to any point of time that you need. فأقدر أعرف what are the voltages of the capacitors after 12 seconds. Or after 20 seconds. I can, at any time that I need to know what are the voltage of the capacitors, I can just apply this and know it. وإذا عرفت the voltage of the capacitors, the current of the inductors, of course, خلاص, I can know everything else about the circuit. Okay, that's why this is extremely important and useful to us, right? Right. Now let's now see this talk in an example, right? So this is the first example that we have here. Look here يا شباب. Determine 5s. هنا it's a little bit easier, right? لأن هنا طلع من إيش؟ ال state transition matrix في frequency domain. Okay. So determine 5s for this system. This system is given by this A, B, C matrices. How about D? معناها إيش؟ معناها D equal to 0. It's not given to me. Actually, this is as you can see in this case, yeah, خلاص, let's keep it like that. طيب. So all I need to do is to find this. So how do I do that? Let's see now. Let's solve this example. So remember, what is 5s? This is what you need. This is something that you need to remember, Ish. Okay, this is not going to be given to you. 5s is equal to Ish. It's equal to Si minus A inverse. Okay, as you can see here, the value of this 5s, it only depends on what? It only depends on the A matrix. See, I don't need the B or the C matrices. Actually, they are putting here just like a trick, right? For this requirement, only for this requirement, you don't need neither B or C, nor C. You only need the A matrix. If you remember also before the week number 8, we said that the A matrix is the most important one. It carries out a lot of information. And as you can see, the A matrix, by using it, I can know what is the transition. It's the transition matrix. This is one of the benefits or applications of why the A matrix is very important. Okay, so I need basically to get this Si minus A. So these are the steps that I'm going to do. First of all, I'm going to find what is Si minus A. Then I'm going to get the inverse. Don't forget about the inverse. So first, we'll say Si minus A. This is the first step. So Si minus A is quite easy. What is Si? Now look, the A matrix here is 2 by 2. And what is I here? And in this case, I is equal to ايش? Is equal to 1, 1, 0, 0. This is the identity matrix. So I choose 2 by 2. Right? So Si means what? It means that Si is equal to ايش? It's equal to S 0, 0. Right? So I'll go back here. Si minus A will be what? It will be Si, which is this. It will be S 0, 0 minus A. What is the value of A? A is here, right? This is A. So it is 0 minus 2, 1 minus 3. معناها ان Si minus A, all of this is equal to what? This is equal to, if I subtract this minus this, what do I get? I get S, so S minus 0, S. 0 minus minus 2, 0 minus minus 2 is what? It is plus 2. 0 minus 1, so minus 1. S minus minus 3, S plus 3. Okay, so we have obtained what is the value of Si minus A. This is Si minus A. Now, again, I don't need to find Sa minus A, I actually need to find the inverse of Si minus A. So now I need to find the inverse of Si minus A. So I need to get the inverse of this matrix. I need to get the inverse of S2 minus 1, S plus 3 minus 1. So how do I do that issue? How do I get the inverse of a square matrix like this? So to refresh your memory, in order to find the inverse from your engineering mathematics course, the inverse is equal to the adjoint. So the adjoint of the matrix. So it's going to be the adjoint of Si minus A, يعني the adjoint of this thing, divided by the determinant. Remember the determinant? The determinant of Si minus A. So in order to get the inverse of Si minus A, I need to know what is the adjoint. I need to know what is the determinant. Okay? Let's start by the adjoint. What is the adjoint of this thing? What is the adjoint? The adjoint of Si minus A. So the adjoint of a matrix is a special operation, and it is very simple for a square matrix, for a 2 by 2 matrix like this. So for a 2 by 2 matrix like this, the adjoint is nothing but what? You go to these two terms, which you call the primary diagonal. So you go to the primary diagonal and you flip the element. So you put S plus 3 here, you put here S. So look, S plus 3, I put it up here. So S plus 3. Well, S heavy, I'm going to put it here. Okay, so I swapped them. And this secondary diagonal, what I'm going to do, I flip the signs. So here this is S, it becomes minus S. This is minus 1, becomes plus 1. So here you switch the elements, here you switch the signs. Like that. This is the adjoint. How about the determinant? The determinant of Si minus A. determinant نسميه ايش يا شباب؟ محددات, right? محددة, right? So Si minus A is this thing. Yeah. So this is Si minus sorry يا شباب. Yes. Okay, so this is, I want to find the determinant of this thing. So this is S. Sorry, this one. S. No, sorry. This is. Oh, made a mistake here. Just a second. Yeah, this should be 2. Sorry, this should be 2, not S. This is 2, right? And this is minus 2. Yeah, sorry, Asha. Right? Okay, so this is 2 minus 1. Again, I just swap these and I change the sign of these. So here we have S. I'll go here, S. 2 minus 1, S plus 3. I want to find the determinant of this thing. The determinant of this thing. Right? So what's the determinant? How do I find the determinant? The determinant is equal to what? We take this multiplied by that minus this multiplied by this. So it will be equal to S multiplied by S plus 3 minus 2 multiplied by minus 1. So this becomes what? It becomes S square plus 3S plus 2. Okay, this is the determinant of this SI minus A. Okay, معناها ايش؟ معناها I come here، معناها ان الانفرس، معناها phi of S اللي هو the inverse of SI minus A is equal to what? It is equal to this, the adjoint, divided by this. The determinant. So the adjoint divided by the determinant. The adjoint divided by the determinant. So it's equal to, I can do that like that. 1 over S square plus 3S plus 2 اللي هو هذا مضروب في ايش؟ 1 over and divide, right? طلعت برا. And now the adjoint is what? It's S plus 3 minus 2 1 S. So this is our state transition matrix. Now I can put this inside. أقدر أدخل هذا هنا. And if you look on this thing, I can actually write it in terms of poles. And this thing I can write it like that. It's okay. But actually I can write this as this, right? I can write like that. S, 2 numbers. You multiply them and you get 2. You add them, you get 3. So it is S plus 2, S plus 1. Right? So I can do that. Yeah, if you like. It's fine. Both are okay. معناها ان ايش؟ معناها ان phi of S اللي هي SI minus A inverse is equal to ايش؟ بدخل هذا هنا. Insert this into the bracket, the big bracket of the matrix. You can write it like that or like that. It's fine. So what do I get? I get S plus 3 divided by ايش؟ S plus 2 S plus 1. Here minus 2 divided by S plus 2 S plus 1. Here I have 1 over S plus 2 S plus 1. And here I have S over S plus 2 S plus 1. Okay, so هذا لو دخلت القوس this inside the bracket I get this. So this is okay, this is okay. This, instead of writing it like that, if you want to write it like that, it's also okay. It's fine. You can write it in whatever shape you like, as long as it's correct. Okay. So this is basically the answer that we obtained here, right? This is the answer that we obtained right here. Now he is going an extra step in the question here. In this example, he's going an extra step. He's actually finding phi of t. So how do I find phi of t? If I want to find the value of phi of t, I need to take this and I apply in the inverse Laplace transform. Okay, we can do that later on, inshallah. But let's for the time being, let's settle for finding phi of s. Okay, inshallah, if we have time at the end, we can see how we find phi of t. Or maybe let's not do it in this example. Let's do it in the next example. If we have no more time, we'll come back and do it here. And in the homework, inshallah, we're going to see how we can find the value of phi of t, not phi of s. Okay, so let's do that. Do this in this example. Okay, it's similar. I think it's similar to the question that we have here. طيب. So we're going to conclude with this example, inshallah. So this is the final example that we're going to be taking for this class, and inshallah next week we'll continue with other operations, right? So let's do this one. And look here, we need to find phi of t, not phi of s. Okay, so we'll start from the beginning. Let me just bring a white paper here. Remember, in order to get this phi of t, the only thing I need is the A matrix, right? So see here is giving me the state space model. I only need the A matrix. So I'll come here, I'll copy the A matrix. A is equal to what? It's equal to 0, 1, minus 2, minus 3. Right? Okay. So our goal is to find the state transition matrix in the time domain. So first we are going to get phi of s. Phi of s is equal to si minus a inverse. By knowing this, by getting phi of s, I just apply inverse Laplace transform, I get phi of t. Okay. So what is the value of this expression that I have here? It's equal to okay. So you can do it in one go. I'll just do it step by step here, but you can do it in one go. Look here, show. I can say this is s. This is si, right? This is si minus a. What is the value of a? It is 0, 1, minus 2, minus 3. So this minus that, what does it give me? It gives me s minus 1, 2, s plus 3. This is very similar to the previous example that we just did, but let's do it anyway. Okay, so I can do that automatically. I didn't need to do this. Look directly. If I have the A matrix like here, I can automatically say it is s minus 0s. Then here 0 minus 1, so I put minus 1. 0 minus 2, so I put plus 2, and then s minus 3. S minus 3, you get s plus 3. Okay. But now I have si minus a. In order to get the inverse of that, I need to get two things: the adjoint and the determinant. What is the adjoint? The adjoint is simple. In order to get the adjoint, I'll take this, flip these, switch these, swap them, and then change the sign of these. So it is s plus 3, s plus 1, minus 2. How about the determinant? The determinant is equal to what? The determinant is equal to s, the determinant of this thing, s minus 1, 2, s plus 3. So what is the determinant of this thing? It's equal to s plus 3. It's equal to this multiplied by this, basically, minus this multiplied by that. So h minus 1, 2. So it's equal to s squared plus 3s. This is minus 2 multiplied by minus, so you get plus 2. So it's the same determinant as you can see. Okay, it means that phi of s is equal to h. Phi of s is equal to the adjoint divided by the determinant. So it's going to be this divided by that. So I'll write it like this. See, I'm going to write this big bracket like this. Okay. What do I have here? I have s plus 3 over s squared plus 3s plus 2. Here I have 1 s squared plus 3s plus 2. Here I have minus 2 over s squared plus 3s plus 2. And here I have this divided by this, s squared plus 3s plus 2, right? So this is the state transition matrix in the frequency domain. This is phi of s, right? Now, how do I get phi of t? Phi of t is simply the inverse Laplace transform of phi of s. So I basically need to get the inverse Laplace transform of that. So how do I do that? I basically need to get the inverse Laplace transform of each one of these, right? Look here, I have 4 components, right? 4 elements. So I need to get the inverse Laplace transform of every single one of them. So this is the first challenge. What is the second challenge? The second challenge is, as you can see, each of these ones you need to apply partial fraction expansion, right? Because this is we don't see this in the Laplace transform table that we have, right? We don't have this in the Laplace transform table. So I need to decompose it using the partial fraction expansion. So this is what we are going to be doing now. But don't get worried, because actually, if you do it once, the other partial fraction expansions are going to be simple, as you are going to see now, as I'm going to show you now. Okay, so these are let me do it like that. This is phi of s that I have here. So I need to get each one of these. And remember, in this case, it would have been better to decompose this. But I actually wrote it in that for a purpose, so that you can see when you reach this point, you need to decompose that. Because in order to apply partial fraction expansion, you need to decompose you need to factorize the denominator, right? So you do it step by step. First, you do this one here. So I need to do it for s plus 3 s squared plus 3s plus 2. Right? So I'm going to write partial fraction expansion. What is this going to be equal to? It's going to be equal to s plus 3, and the denominator is going to be, as we did in the previous example, it is s plus 2, s plus 1. Two numbers, you multiply them, you get 2, you add them, you get 3, right? So it means that when I decompose this, it will be a over s plus 2 plus b divided by s plus 1. Now you can apply any of the techniques to find a and b, but I advise to use the technique that we have learned before. So how do I find the value of a? A is equal to this, which is this one, multiplied by s plus 2, right? So a is equal to s plus 2 multiplied by s plus 3, s plus 2, s plus 1. And I substitute at s equal to minus 2. This will cancel with that. So what do I get here? I get minus 2 plus 3, I get 1 divided by minus 1, right? So I get 1 divided by minus 1, I get minus 1. How about the value of b? The value of b is equal to what? It's equal to s plus 1, s plus 3 over s plus 2, s plus 1. And I substitute at s equal to minus 1. So this will cancel with that. So I get here 3 minus 1, 2, divided by 2 minus 1, 1. So 2 over 1, so you get plus 2. Means that this whole thing, I can write it as what? I can write it as minus 1 over s plus 2 plus b, which is equal to 2 over s plus 1. So now I have opened this, right? I found what this is. I can easily know what is the inverse Laplace transform of this, right? Very straightforward. This is going to be minus e to the power of minus 2t. This is going to be 2 multiplied by e to the power of minus. We're going to do that. But let's get the other elements here. Okay, so we found this. This is the first element, 1. Now let's do the second one here. This one. 1 over s plus 2 s plus 1, right? Decompose it, becomes like that. So it will be a over s plus 2 plus b over s plus 1, right? So in this case, what is the value of a? A is going to be s plus 2 multiplied by 1 over s plus 2, s plus 1. substitute it at s equal to -2. So this will cancel with that. What do I get here? -1. Right, how about b? B is equal to s plus 1, s plus 2, s plus 1. Substitute at s minus 1. So this will cancel with this. So what do I get here? 1 over 1. So you get 1. So this is equal to h 1 over s, sorry, minus 1 over, because this is the value of a, s plus 2 plus 1 over s plus 1. As we found, we decomposed this one here. Then 3. C#, it is not complicated, but it's a little bit time consuming. But inshallah, and if you have an example, or if it comes in a quiz or an exam, and you most likely are going to see that sometimes these terms are going to be zeros, or maybe these two are going to be zeros. So you don't need to do you don't need to do the partial fraction expansion several times. Okay. Right, let's finish up now. The value of here is going to be minus 2 s plus 2 s plus 1 a s plus 2 plus b s plus 1. The value of a is equal to s plus 2 minus 2 s plus 2 s plus 1. This will cancel, substitute at s minus 2. So what do you get here? Minus 2 divided by minus 1, you get 2. Here we have b is equal to s plus 1 minus 2 s plus 2 s plus 1 is equal to minus 1. This will cancel with that. So what do you get here? 2 divided by minus 2 divided by 1, so you get minus 2. It means that this whole thing is equal to 2 over s plus 2 minus 2 minus here minus 2, or can put it like that so that you don't confuse yourself. Like that. And lastly, you need to get this element, right? So for s plus 2 s plus 1 equals to a s plus 2 plus b s plus 1 equals to, let's find the value of a, s plus 2 s plus 2 s plus 1, substituted at s equal to minus 2. See what you get here? Minus 2 divided by minus 1 equals to 2. How about the value of b? B is equal to s plus 1 s plus 2 s plus 1 at minus 1. Cancel. Get minus 1 divided by 1, so you get minus 1. It means this is equal to 2s plus 2 plus minus 1 s plus 1. So now we have decomposed all 4 of them. Alright, so yeah, we have decomposed these 4. These 4, each one of these 4, we decompose them here. 1, 2, 3, 4. So now I can find the final solution. By saying that 5s, instead of writing them in this form, I will write the decomposed form of each one of them. So here, instead of writing this, I will write this. Actually, let me, so that we don't forget. It's equal to s plus 3 s squared plus, let me write at s plus 2 s plus 1 s plus 2 s plus 1 minus 2 s plus 2 s plus 1 s plus 2 s plus 1. Now I'll open up each one of them according to the partial fraction expansion expressions that we got here. So what do we get? We get the first one from here. I'll write it as ايش? minus 1 over s plus 2 plus 2s plus 1. Second element, this one, it is minus 1 s plus 2 plus 1 s plus 1. This is the second element. Third element, this one here, is equal to 2 over s plus 2 plus minus 2s plus 1. And lastly, the last fourth element right here, 2s plus 2 plus minus 1s plus 1. So this is phi of s. Now the final step, finally, after a long mathematical operations, now we can find what is phi of t by taking the inverse Laplace transform. And you do it, and by now hopefully you should know how to get these without even using the table, or you can always use the table. So what is this? This will be this will be minus e minus 2t, right? How about this? Be plus, this will be 2, this 2. Then what is the inverse Laplace transform of that? It is e minus t. Okay, how about this? How about this issue? This is minus e minus 2t plus, how about this? E minus t. How about this one? It's 2e minus 2t minus 2e minus t. And finally this one is 2e minus 2t minus e minus t. Okay, and this is the final solution. This is phi of t. If you take this, if you multiply by initial conditions, and this is the final answer. But if you want, for example, if you have x1 of 0, so for example 1, and x2 of 0, so also 1, take them here, x1 of 0, x2 of 0, which are these two values, put them here, you multiply them, you get instead of getting, you are going to go from x1 of 0, x2 of 0, you are going to get the values after any time that you like. You are going to get some expression. Here you have x of t, right? You put here 1, you get after 1 second. You get the values of x1, x2 after 1 second. You put here 5, you get the answer after 5 seconds. You get 10, you get the answer after 10 seconds. Okay, you get the state of the circuit after 10 seconds. And this is why this thing is very important. But then for the time being, one of two things. He's going to either, like in the questions, he's going to either ask you to find what is 5s, and this is going to be the easiest, the simplest one. But of course, you don't. If asking you about finding 5s, you don't need to apply partial fraction expansion like that. We can just stop at this point. You found 5s, that's it. You stop here. But if he does not ask you to find 5s and instead ask you to find y of t, then you need to open this. You need to find the inverse. You need to get the partial fraction expansion of each one of them, each one of these elements. Then, because these are not available in the partial fraction, the Laplace transform table. After you do partial fraction expansion, you get something like that, and now, something like this after partial fraction expansion, and now it becomes very easy to get the inverse Laplace transform from the table. So now you get phi, you get the value, you get phi of t. Okay, So what did we learn this? This lecture? We learned three operations. We learned if I have the differential equation of the system, how do I get the system state representation, A, B, C, D matrices? If I know the transfer function of the system, how do I get the A, B, C, D matrices? And lastly, the last thing that we just did now is how do I find the state transition matrix? Either in the frequency domain, like this, or in the time domain, the state transition matrix, which is extremely important, because as you have seen, by knowing the state transition matrix, I can go from the initial conditions to any point in the future. I go from x1, x0 to x1 to x2 to x5. I can get to any point of time in the future just by knowing the initial conditions. Okay, so next time inshallah. So this is the solution of this example. خلاص, it's solved here. I will scan these, put them in the, I'll put them in order. Okay, so I'll put the slides with my notes that I wrote here in the papers. I will put them in the I'll scan them together and put them in the on the Blackboard. So go to the Blackboard. You're going to see a new tab. It's called online learning. I will also post the assignment, but the assignment I'll post it after we finish this whole chapter, right? So I'll put the assignment after we finish this whole chapter. We still have a few topics that we need to discuss. So next time, inshallah, we're going to start from this part. It's not going to be that difficult. It's not going to take us that long. So we'll start from here next time, inshallah. So best of luck, inshallah. And if you have any question, you can send me an email or talk to me on the WhatsApp group that inshallah is going to be created, or send me, or you can use the discussion board on the Blackboard. So thank you.